So therefore, continued from there, I have the equation of tangent which reduces to xx1 plus yy1 minus 3x minus 3x1 plus 2y plus 2y1 minus 2l equal to 0. This, on further simplification, gives me this and this when taken with x common, x1 minus 3 of x, and this with y, y1 plus 2 of y, and this, and the constant plus minus 3x1 plus 2y1 minus 2l equal to 0. Now this is equation of tangent t, which is obtained using the formula s equal to 0. But the equation of tangent is already given to be 4x minus 3y plus 7 equal to 0, which is also the equation of the same tangent t. Therefore, these two lines must be same. So if I take this as 1 and equation 2, I clearly understand that 1 and 2 represent the same line t. They represent the same line t. Therefore, their coefficients must be in same ratio. Therefore, x1 minus 3 by 4 must be equal to the y coefficients which are in same proportion, and the constants minus 3x1 plus 2y1 minus 2l by 7. They should be in same proportion, through which we find x and y. So let's try to find x1 and y1 from these two equations. So as I take these two equations, I have in cross multiplication minus 3x1 plus 9 as 4y1 plus 8. This 3x1 plus 4y1 is 1 when on arranging the terms. Then I have the first and last equation which I take, and then on simplification gives me 7x1 minus 21 is minus 12x1 plus 8y1 minus 48. This on cross multiplication gives this equation. Now 12 plus 7, which is 19x1, and minus 8y1 is minus 48 plus 21, 31, 41, which is minus 27. So this I get as equation 1, equation 3 and equation 4, where equation 3 and 4 are solved using the elimination method. So I multiply this equation with 2, and then I get 2 times of 3, which is 6x1 plus 8y1 equals 2. This on adding gives me 19 plus 6, which is 25x1 is minus 25. That implies x1 is equal to minus 1. So I get the value of x1 is minus 1, which I substitute here. Therefore, substituting in 3, I get 3 times of minus 1 plus 4y1 equal to 1. That implies 4y1 equals 1 plus 3, which is 4. That implies y1 equals 1. So x1 is equal to minus 1 and y1 is equal to 1. Therefore, the point of contact the required point of contact is P, which is x1, which is minus 1, and y1, which is 1. So this is the required point of contact, which we find using the concept of S1 equal to 0 and the proportion which gives the values of x1 and y1. The point of contact can be found in this method. Now let's find the equation of chord where the points are given in parametric form. So now that we have considered the topic of parametric form of the points on the circle in the previous session, so let's recap with finding the equation of chord in parametric form. So we know that a parametric form involves the radius and the angle which we consider for the point. So therefore, for the circle S equal to 0, if I have 2 points where a chord is formed, where this is A for θ1 and B which corresponds to the angle θ2 for the circle with radius r, then we know that θ1 corresponds to the point minus g plus r cos θ1 and minus f plus r sin θ1, and the point B with the angle θ2 corresponds to the point minus g plus r cos θ2 minus f plus r sin θ2, 0 less than or equal to θ1 and θ2 less than or equal to 2 pi. So with these 2 points, I want to find equation of chord, which is given by AB, which is given by x plus g cos θ1 plus θ2 by 2. Then this is y plus f sin θ1 plus θ2 by 2, which is r cos θ1 minus θ2 by 2 is how we understand the equation of chord given by this formula, where the 2 points, the endpoints of the chord, are considered in parametric form as a θ1 and a θ2. So equation of chord is this in parametric form for the circle S equal to 0. Similarly, let's see the equation of tangent in parametric form for the polar coordinates r, theta. Say for example, I have a circle S equals 0, and then I have a tangent T at P theta. So let me say the polar coordinates of the point P, the point of contact of the tangent with the circle, is theta, and let radius of the circle be r. Then with r being the radius of circle and theta being the point of contact, I have p theta, which is given by minus g plus r cos theta minus f plus r sin theta. Therefore, with this point, equation of tangent T at p theta is given by x plus g of cos theta plus y plus f of sin theta equals r, where r is the radius and theta is between 0 and 2 pi. So equation of tangent at theta is given by x plus g cos theta plus y plus f sin theta equals r. Now let's try to find the equation of tangent in standard form. That is, if I have a circle with radius r and center as origin, that is, if the equation of circle is x squared plus y squared equals r squared, then for the point p theta equals minus g plus r and minus f plus this reduces to r cos theta and r sin theta, since g and f are equal to 0, they vanish. Now therefore, for this point r cos theta and r sin theta, equation of tangent t at p theta for the circle x squared plus y squared equal to r squared, equation of tangent at this with respect to the circle x squared plus y squared equal to r squared is given by x cos theta plus y sin theta equals r, is how we understand the equation of tangent at point p theta for the circle x squared plus y squared equal to r squared in standard form. X cos theta plus y sin theta is equal to r in parametric form. So now that we have defined the tangent, similarly we define the normal. The tangent and normal are always associated with each other. Wherever there is a tangent, there is a normal, and wherever there is a normal, there is a tangent for the circle. So let's see what is the normal for the circle. So before we understand the normal, let's recap with the tangent of the circle s equal to 0. So I have a circle s equals 0. So for this circle, let me draw a tangent at P. So this is the tangent at P, x1, y1. So if this is the tangent for the circle, then a line which is perpendicular and passing, any line perpendicular to the tangent and passing through point of contact is the normal. There are infinitely many lines which are perpendicular to the tangent, but there is only one line which is perpendicular to the tangent and passing through P. That is, it passes through this. This is the normal. This is the tangent. So we understand that a line which is perpendicular to the tangent and passing through the point of contact is the normal. So in this case, this is the normal. But there is a very important geometrical property we need to understand, that the normal always passes through center of circle. So normal is perpendicular to tangent and normal passes through center of circle. Because radius is perpendicular to tangent, this being the radius will pass through the center of circle. So we always have n perpendicular to t. This is how we define the normal connected with the tangent and passing through the point of contact. It is very important to note that a normal has a very basic peculiar property, that is, since there are infinitely many lines which are perpendicular to tangent, there exists only one line which passes through the point of contact Px1, y1 and is perpendicular to T. Therefore, I can say with this property that for every tangent there is only one. Therefore, for every tangent there exists one and only one normal, is how we understand this property. So every tangent has only one normal which it passes through. There cannot be two normals for one tangent. So the normal being this perpendicular to and passing through Px1, y1, the point of contact. Uniqueness of the normal of the tangent T. Now let's derive for equation of normal of the circle S equal to 0. So we know that for the circle, the general circle S equal to 0, I have the normal which passes through the point of contact and is perpendicular to tangent. I have to find equation of this line which is the normal. So in order to find equation of this normal, that is the line, I have the formula before which we have the general circle, that is x squared plus y squared plus 2gx plus 2fi plus c equal to 0. Now the point of contact is Px1, y1. Now for this point of contact, my equation of normal n is given as the formula x minus x1 into y1 plus f minus y minus y1 into x1 plus g equals 0. This is the equation of normal at the point Px1, y1, at the point of contact Px1, y1. So equation of normal is given by x minus x1 times y1 plus f minus y minus y1 times x1 plus g equal to 0, where x1 and y1 are obtained from this and f and g are obtained from the general equation of the circle S equal to 0. Now let's derive for equation of normal for standard form of a circle. That is, if the circle has center as origin, that means, and the radius is r, then in that case the circle has the equation in the standard form as x squared plus y squared equal to r squared. So for a circle in standard form, the equation of normal n at Px1, y1 with respect to the circle x squared plus y squared equal to r squared is given by the formula xy1 minus yx1 equals 0, is how we have from the standard form of the circle. xy1 minus yx1 equal to 0 is the equation of the normal. Now let's see the angle between the two tangents for the circle S equal to 0. So how is the angle formed between the tangents is the biggest question out here. So for example, I have a circle S equals 0 and I have a point Px1, y1 outside the circle. Then from this external point, we have already discussed that there are two tangents which can be drawn from a point outside the circle. Therefore, the two pair of tangents are given by one this and this. So the two tangents are T1 and T2, which give the angle. So this angle can be formed using the relation. If this is theta for the circle, then theta is the angle between the tangents T1 and T2, which is given by the relation tan theta by 2 is equal to r by root S11, where r is radius of circle S equal to 0, and P x1 y1 will decide the point this, and theta is given using the relation tan theta by 2 equals r by root S11. Is how we find theta, the angle between two tangents of a circle. Chord of contact for the circle S equal to 0. So what is the chord of contact? As we know that the chord is the part of the circle, the line which cuts the circle into some segment, then we have the chord of contact defined in the similar fashion. Let's see how the chord of contact is defined for a circle. I have a circle S equals 0, and I have an external point P x1 y1 from where I can draw the two tangents T1 and T2, which make the point of contacts as A and B. Now, as we know that from an external point there are two tangents which can be drawn to the circle, that is, there are 2 points of contacts. Those 2 points of contacts just join to form the chord. So this kind of a chord which is formed from an external point being considered with two tangents is called the chord of contact. So this is called chord of contact. And equation of chord of contact at P x1 y1, for P x1 y1 with respect to the circle S equal to 0 is given by S1 equals 0. So the equation of chord of contact is S1 equal to 0, which is obtained from an external point from where the two tangents are drawn. The chord of contact with the equation S1 equals 0. So let's connect the chord of contact with respect to position of a point. Now that we know that the position of a point has 3 cases. One is the point outside the circle, the point on the circle, and the point inside the circle. So if I consider all the 3 cases, case 1, case 2, and case 3, I have the circle from where an external point. For case 1, I have P outside the circle where I get 2 tangents which can be drawn. So I get 2 points of contacts where I can join this. For case 2, where the point is on the circle, I have this on the circle where I have only 1 tangent. Now case 3, where the point is outside the circle, where the point is inside the circle, I do not have any chord of contact. So these 3 cases gives me the consideration that for an external point AB is the chord of contact. And for the point which lies on the circle, tangent T itself is the chord of contact, because this itself acts as the chord of contact. Now for this, there is no chord of contact through P. No chord of contact of P x1 y1, because P x1 y1 lies inside the circle. Therefore, we get three cases where if P lies inside the circle, there is no chord of contact. If P lies on the circle, the chord of contact is the tangent at that point itself. And if P is outside the circle, the chord AB is the chord of contact of P x1 y1. Is how we understand the chord of contact of each of the positions of P outside, P on, and P inside.